speak about alternating proximal gradient descent for non-convex regularized problems with multiconvex coupling terms.
Thank you for the presentation. This is a joint work with the lady who finished her PhD 1 year ago with Antonin. Let me go to the menu. So I'll make a general presentation of the methods that the most popular method to solve this kind of problem. I'll mention something about the state-of-the-art algorithms. I will present why we choose to do something different. We will see practical examples, how to do, how to use these functionals and this algorithm. I'll have some reminders. Let me mention then at point 4 we have a full overview of the motivation of the algorithms, and then I will stick on some ideas about the convergence proof, and then I will present an application. So the problem that we consider is to minimize. Suppose that we have real vector, or for instance images on a real finite dimensional real space, and that they are decomposed by blocks, and that for each block we have a different possibly different regularizer, and that we have coupling function H, which we will suppose that is block multiconvex. It means that for each block Zi, this function is convex. Now let us mention that typically the joint coupling function is not convex. The function Fi are regularizers, and then can be convex, non-convex, what you want. We will use some regularity assumptions naturally. There are many applications that I briefly list is given here. They are well known, blind deconvolution, matrix factorization, but the application I will show is a little bit different. So let us, for two blocks, the same optimization problem is written this way. X and Y are the two blocks. They belong to finite dimensional spaces. H is supposed to be a block B convex. It means convex with respect to X and convex with respect to Y. And F and J are regularizers. When I write, if I write everything with the multiconvex term, I'm afraid that the expressions are extremely tricky to understand and not easy to read. So I'll present most of the material for the two-block problem. I'll give a few slides how this generalizes to n blocks. The most intuitive way to solve such a problem is to apply just a block coordinate descent. What it means that you have to minimize with respect to X and with respect to Y. To descend, you have to choose an algorithm to solve the X step and an algorithm to solve the Y step. This is something which is very, very old. Let me mention that if the functions are real analytic, there are some general convergence results that were obtained in 2006. Well, without these real analytic assumptions, convergence can be ensured under some conditions, Another method is the proximal regularization of the BCD. And here again, we have to choose an algorithm to step the X and Y update. We can choose the step sizes, and then we compute, we iterate over X and K. What is the most, in fact, in both algorithms, we have to use an external program, an algorithm, which is a source of many numerous errors, because it means that to solve the X step, you have an iterative algorithm. You have to decide about the stopping rule, when to go, and then to go to the next iteration. Then you have to make another minimization algorithm, and then the final result will be subject to the errors that are accumulated inside the steps done by this external algorithm. So in some sense, both schemes are in some sense abstract. The algorithm is not complete, is a little bit abstract, can be said to. So recently, well, not so recently, 4 years ago, there was the idea to use somehow the regularity of the function, the coupling function H, so that it was possible to obtain explicit updates. The method was introduced independently in two papers. For each iteration, you have to find step size according to the Lipschitzian of the current gradient of the coupling term, and then you have to solve this problem. What you see that it is, if F is prox friendly, we will have an explicit step. And then for the next step is similar. We have to find a sigma k according to the gradient, to the Lipschitz constant of the gradient of the coupling term, and then we minimize with respect to y. Again, so we see that iterates will be are explicit whenever f and j are prox friendly, in the sense that this function has an explicit closed form solution. These algorithms, compared to the previous methods, these algorithms really gave a tremendous improvement with respect to the existing algorithms, and they were followed by many other authors. Let me mention that André Repeti, several participants to this conference also used this approach. Thomas Bock, André Repeti, Jean-François Augel also tried to use it. So there is a lot of interest. Let us see what is in something more in detail. A main tool for the convergence of these algorithms, in order to obtain the convergence of the whole sequence to a critical point of the objective function, the Kurdyka-Lojasiewicz property that I will mention later on was used. Let us now see what are the choices for the coupling terms, which are usually data fidelity term, and choices for the functions f and j. H is most often a biquadratic or multi-quadratic function. Sometimes there is a bilinear term. And we can see that in all applications, the gradient of h of the coupling term is only locally Lipschitz. So this means that the the step sizes that have to be computed at each step can, at each iteration, can vary quite a lot. Also, it is not very okay. An attempt to fix this was to apply a preconditioning. It was yesterday briefly mentioned by André Repetit. The regularizers that are used are quite simple. Let us mention that if in case if f is really non-convex, for instance, the L0 norm was used in the paper on PALM. Then you see that you have several minimizers. Then you have to choose one of them. So let me present a kind of motivation about the proposed algorithm. This is only the academic motivation. So we can say, well, we would prefer to have iterates that are uniquely defined, and you would prefer to have step sizes that can be fixed and that do not need to be updated at each step. What we do is that we use the strong property that the coupling term is biconvex or multiconvex, and we change the splitting. To this end, we suppose that the functions f and j are differentiable on their domain. In the new days, everybody is speaking about non-differentiable and so on. Let me mention that from a numerical point, if you want that f and j are non-differentiable, you can also use the differentiable approach, approximation, faithful. The question was studied by many persons, and there are many authors who make whose papers are up to the numerical results. Everything is non-differentiable, and in the numerical part you have a differentiable approximation of the objective function. But however, there are some studies that show that what is the error if you approximate a non-differentiable function by a differential one. What are the errors? What is the speed improvement? How an optimal unified framework, how to obtain smooth approximation, was also provided by Beck and Taboo. And finally, that in many cases you just do not want a differentiable function, which is our case. Let me come to the practical motivation. 1 year ago, nearly, a little bit less, we were given some images. This is the observed image, and the images come from our industrial partner Onera. Oh, I have to turn. They come from our industrial partner Onera, and this is not a really ground truth because it was computed using a protocol from a sequence of well-calibrated, I don't know, but we had only 9 images like this, and you can see that there is a fringe pattern that appears. In order to apply some image processing tasks, stereometric or something like that, in order to obtain some other information from the observed images, the first goal is to remove the fringes. We have considered this model, multiplicative model. What is known from the shear letters device is that the fringe the Fourier transform of the fringe has belongs to interval in the in the vertical direction, and where these frequencies can be estimated quite faithfully. Furthermore, we know that the fringes are bounded, and finally, for images, here is a town image, we have forest images, we have landscape images, and so on. So in general, there is no reason to suppose that the gradient of these images should be sparse. So we considered a problem like this. We defined a coupling function like this, regularizer like this, and here we inserted the constraint of on the Fourier transform. In order to avoid that the gradient is sparse, we used an edge-preserving function, which was differentiable, and we did an algorithm which was submitted and published a few months ago. But we did an algorithm, but it was now I present how it is generalizing, and I present the proof of this, which was submitted just a month ago. So what is the algorithm? Compared, it is we set the step sizes are fixed in advance. They depend only on the Lipschitzian of the regularizers. They are fixed, and for each step we have to minimize these functions. Clearly, that if f or g is 0, the step sizes are just positive numbers. Compared to the previous scheme, the Prox linearized scheme, what we have to compute here is the minimizer of this. In most applications, when h is a biquadratic function, we have a Prox-friendly term. This is just to solve a well-posed quadratic function to find the solution. So the iterate xk and yk are well defined, unique, because they are the minimizers of a strictly convex and coercive function. Finally, the regularizers f and j can have very complex structure because they're not involved in the we just at each iteration only their gradient is taken, and no explicit minimization is taken with respect to f and j. Do you want me to compare with the previous algorithm to see about the simplicity or not? Yes or no? This is the state-of-the-art algorithm, and we arrive with something like this. So let me see what are about the notation. This always will denote the Frobenius norm. I do not write everywhere f because in some cases we just took the images column-wise, so this is not needed. The optimization model, as I mentioned, I will consider basically the big two-block problems because things are much easier to present. What are the main assumptions? That G is lower bounded, that F have gradients with that are Lipschitz continuous, and that H is biconvex and differentiable inside its domain. I wrote on, okay, inside its domain. Another way to write the assumption is in this way. Here, H tilde represents the smooth part of the coupling term, but we can add to the coupling term the convex constraint on x and on y. What can we do with what are the functions that we can consider and that fit our application? For a general family of functions that can be optimized using our method is this one. Here, about the coupling term, these are bilinear forms. HK are convex and differentiable functions. They can be usually, in most of the papers on the related topic, it is just the function t square. Dx and di are closed non-empty sets. These are the constraint sets. AI and Bj are general linear operators. And I will give some functions for the functions fi and j that are in accordance with the assumptions. I have several examples. There is a long list. All of them are used in different papers. We can notice that all these, when alpha goes to 0, become very stiff near the origin and can provide some approximation of non-smooth functions. In particular, the functions 5 and 6 can approximate the counting function. The functions 2 to 4 are convex, and for alpha, this one, are convex, and when alpha goes to 0, they approximate the L1 norm, and accordingly, this is very popular nowadays. People are using C power P for P smaller between 0 and 1 to approximate the corresponding LP pseudonorm. So I just mentioned that the main tool for the convergence of in the papers that I mentioned before was the Kurdyka-Lojasiewicz inequality. So I will start just by recalling what it is about. I will consider here the case of subanalytic functions and not the case of semi-algebraic functions, which, just because this is a more general context. So functions, I took the definitions from the paper of both Danilidis and Luis that was published in 2007, and that was the first one that introduced the Kurdyka-Lojasiewicz inequality in order to solve non-smooth problems. In fact, the non-smooth problem was, in fact, it involved constraint. It was smooth inside its domain. So a function satisfies this property. Here, x is a critical point, and x is a non-critical point. So what we need, we have a neighborhood of the critical point. Here, this is the distance between 0 and the subgradient of the non-critical point. We need a constant here, and this should be larger than the value of x minus the value of x at the critical point. Intuitively, this means that you can in some way unfold the minimizer so that it can be reached. And in the paper of Apsil and the others, it is extremely well explained why the Kurdyka-Lojasiewicz property helps to avoid cycling around a local minimizer. A result that was obtained in the paper that I mentioned is given here. If the function is a subanalytic with closed domain, and if it is continuous on its domain, if x star is a critical point of the function, then there is an exponent theta, there is a neighborhood such that, and a constant kappa, such that the Kurdyka-Lojasiewicz property holds. I forgot. I will not enter into technical details about subanalytic functions. I will only mention that real analytic and semi-algebraic functions are subanalytic functions. Because that's everything that we will use in the on the next slide. So we want to obtain something about the Kiel property of our objective function. In order to so as I showed it, we have a function of this form with functions like this, and now we know that if to function, we have to know something about how these all these functions are have some pieces that are either semi-algebraic or real analytic, but we have to know how to combine them, how to make the sum, in order to ensure that everything is subanalytic. And we will use these two facts, saying that if f and j are subanalytic and lower bounded, then the sum is subanalytic. And the other important property that enables us to say that if we make a combination between two subanalytic functions, the result will be subanalytic, under very reasonable assumptions that are easy to prove for the functions that are on the previous page. Yes?
Smaller than 1, the function is subanalytic?
Pardon?
Only for p smaller than 1, that the function is subanalytic?
P smaller than 1?
Yeah, in theorem 2. If the p is smaller than 1.
I cannot say this.
In theorem 2, you have to side to the p. Third line from below.
The p, p. Yeah, it was in the example.
Yeah, I'm wondering if it's smaller than 1.
No, yeah, it can be small. Yeah, people are interested when it is smaller than 1. Yes. There are many papers from Chen.
Yeah, sorry, I didn't mind it. If it is really small, then you need a quadratic term to make it subalgebraic.
It is when p is a rational number, it's very easy to show that if psi is subanalytic, psi p is also subanalytic. And using this property, we could show that all functions psi and psi p are subanalytic, that the function j in the example is subanalytic, and thus it satisfies the Kurdyka-Lojasiewicz property at its critical points. Let me go to the next. Do we have time for some reminders? Do you want to? I did some reminders about subgradients of convex functions, the subdifferential of our convex functions, of our functions, given the fact that the coupling term is biconvex, is given of this form. What we will use is I recall here the proximity operators. We will use in the proofs somehow the proximal inequality. The proximal gradient algorithm maybe you remember is defined in this way. It is a unique. It can be seen as the finding the next point using a proximal gradient algorithm can be seen as the minimization of a quadratic approximation of the function around the current point u. This is quite useful for a better understanding of the algorithm, and from here we can clearly see that the point x plus will be always defined and always belongs to the domain of h. And our iterations were very, very similar. The sufficient decrease lemma, this is the new iterate, this is the old iterate, and you see that this will be very helpful in the proofs. We will largely exploit this fact for the convergence proof. And let me go to the next. The algorithm in the case of biconvex coupling term has the following simple form. Step sizes are fixed in before, and we have the prox with respect to h at the current point y k minus 1 y of something which is simple to compute here, and similar for yk. We take the proximal with respect to h at the point xk, and the proximal, and then at the current point is here, easy to find. The iterates are uniquely defined, and all for n. Okay, let me don't. Maybe I repeat too many. In the case of n blocks, only the writing is a little bit more intricate, but you recognize the same approach. Here is the coupling term, and here are the regularizers, and the functions phi, similar as before, have a part which is Lipschitz continuous, who has Lipschitz continuous gradients, and have some constraints that are closed convex sets. If we have can choose different updating rules. According to the update rule, for each k, you have to choose pick an index between 1 and n, according to the rule, and you just do the same, where the prox is you fix all the zi except the zi, and you compute the prox with respect to the zi component, and this is the full algorithm. So let me come to the convergence, some facts about the convergence. Here, this constant here, you can maybe remember that it comes directly from the decrease lemma, directly. The sufficient decrease lemma. So it is, let me come back. This is the decrease lemma. You see this term. It is necessary so that you have decrease of the quantity fh plus fh. And here we have the same, but we take the minimum because we have two steps. So we have a series. It is not so difficult to prove that the value of the function converges this is a fully descent method, and we have some result that like this, that this is naturally not sufficient for convergence of the sequence, but it's already a good point. Furthermore, we know that at each k there is a subgradient pk of belonging to this function, belonging to the function, to the subgradient with respect to x at the point xk yk minus 1, and here a subgradient belonging to the subgradient at the next step with respect to y at the next step. And we know that these subgradients tend to 0, are bounded by xk minus 1 minus xk, and from the previous proposition we know that this quantity goes to 0. So these quantities also, this subgradient will go to 0. Something that we can say on the set of the limit point set of a sequence, it is, is defined in this way. This is the set of all points for which there is a strictly increasing subsequence of indexes such that there is a convergence subsequence. And we can say something more about about the algorithm. We know that we can prove that there is a subsequence, a convergent subsequence. We have to assume that the iterates generated by the algorithms are bounded, as in many other papers. It amounts to assume that the limit point set is non-empty bounded. In this case, we can prove that we have the sequence of points goes to the critical point, and that 0 belongs to the limit point of the subdifferentiable, which means that we converge to a critical point of f. Furthermore, we know that the set of the limit points from a point starting at x0, y0 belongs to the set of the critical points of the function. Furthermore, the distance between xk, ik, ak and the set of the limit points tends to 0, which is a very important fact already. Because if we have some other additional knowledge on the function, we can from here draw a direct conclusion about the convergence. Maybe I have to speed up, or yes or no? Okay. In order to prove the subgradient convergence, we need to suppose that the smooth part of the coupling term is one-sided locally Lipschitz continuous, which is quite a looser requirement compared to other papers. You notice that here the x is the same. This is because of the splitting that we have used, and we can obtain this subgradient convergence results when we have n blocks. Things are basically unchanged. We have done the proof only in the case when the updating rule is sequential. Otherwise, everything is just rewriting with z and in a more complex way what we had in the previous case. So I will skip easily this part maybe you can recognize that this is the same as before, this is the same as before, but just with more tricky notation. Similar for the subgradient convergence. And in all cases, if you fix n equal to 2, we come back to the biconvex coupling term H. Let us make a summary of what we had. The general functions we consider obey the Kurdyka-Lojasiewicz property. Under the assumptions, only the simple assumption, we know that we have a sufficient decrease property. If we assume that the sequence is bounded, then we know that we have this kind of continuity properties, and we know that we have subgradient convergence. The final proof is based on a result that was established by Tuch, Bolte, and Zweiter, and all these points are the necessary requirement to apply this theorem, and following this claim, we can just establish that the sequence produced by our algorithm is a Cauchy sequence. And we have also this property that the sum, in fact, it is called the so-called finite property. So the assumption, this one was the very basic one. This one, the additional assumption on the continuous part of the complete term. We have the additional assumption that the iterate must be assumed to be bounded. We have a forthcoming paper about this point, but it is not yet published. And we know that our functions have the TL property, so that's clear. Let me go to an application. We consider for a Hadamard product component-wise with two constraints. The constraints are of this form, and the proxies are of X, H are very easy to compute. And this gives rise just to this algorithm, which is extremely simple to compute. These are only component-wise, in a component-wise direction. Let us see how this can be applied from the fringe removal problem that I mentioned. Images W again. We had treated images given by the ONERA, shear lattice images. They are produced by a Fourier transform spectrometer. We had to remove the fringes. What we know is that the 1D Fourier transform of the columns belong to an interval that is we can estimate quite faithfully. The fringes have a range constraint, so the optimization problem we consider is of this form. Here we are. This term ensures the. Let me mention first that using a multiplicative model was quite new in this field, and this gave rise to very small perturbation terms. I will give some illustration later on. And in this case, applying only the constraints, these constraints gave us a very good initialization. So the optimization model, we have regularization over X, Y in the space domain. This term ensures the Fourier constraint. This is the data fidelity term, and this ensures the range constraint. This is an image of size. We had thousands of images of size, the various sizes for the shear letters 2. I think all the images were of this size. I present just a zoom. This is the image that was acquired by the imaging device. The PSNR is something like 21. This is the images obtained by using the proposed algorithm. The PSNR is 59. This is the fringes that we recovered, and this is the reference compared to the reference. So you see that there is not much difference. But we had the references only for 9 images. So I'll present some images without reference, and industrials told us that they are good enough. They are different landscapes. These are from different other sequences of shear lattice images. This one, I do not know what is exactly that. It was something a river or something like this. This is the result of our algorithm. This again, these are only I present only zooms. And at the last part, I will compare for this incoming, this observed image. The traditional model wants that people use an additive model for the x and y component, and with an additive model you cannot get very good result. The multiplicative model is we obtain this result. Let me conclude. Then a new simple algorithm that seems flexible and it's simple to use. Thank you.
So we can take one question. Yes.
So if I understand correctly, the main difference to the Palm algorithm is that your coupling is fully prox operators, right?
Yes.
And now my question is, it is well known that if a function has a Lipschitz continuous gradient, you can write it as a prox with respect to a different function.
Yeah.
So now my question is there an equivalence maybe between both algorithms?
No. No, not really.
Because when, I mean, carrying out the prox with respect to a function is equivalent to taking gradient descent step of a different function. There's a one-to-one correspondence. So maybe you can write it, both algorithms in an equivalent way, but I'm not sure if this is true for this biconvex coupling term. For one function, it's definitely the truth.
Here, what is important is the main difference in the proof is that, for instance, is that you have to you don't have the gradient of the coupling term at the same time. You use it in 2 different ways.
Yeah, you used yeah, but I am saying that the prox coupling term can be written in an equivalent way as the coupling term in the Palm algorithm with alternating
This
gradients.
may be possible, but this will be very interesting to rewrite the prox. If it is possible, I will try this, because this will be very interesting if it was possible to avoid the computing the Lipschitz constants in the prox linear algorithm. This is a very good idea if it is possible to rewrite it in this way. I'll try. Very good idea. Thanks.
Okay, more questions in the coffee break. Is that
Okay.
yeah. Okay. Thank you very much.